Okay, so there was a question about homework number 20 something or other. Which one was it, Thea?
21.
21. Homework question number 21. And this was one where you're given a differential equation and a y1, and then you need to find the other one. So it's a reductional order question. And once you get to the reduced, it's going to look a little bit like what I've got up on the whiteboard. So we did a little substitution where z is actually equal to u prime. And so we're at this point. Now we know what we need to do. We're going to have to integrate. So we need to do the integral of cotangent square root of x over the square root of x plus 1 over 2x, right? And then, of course, we need to make that negative and then take e to that power. The second part's not a big deal. The 1 over 2x, that's just going to give us the 1/2 natural log of x. So 1/2 natural log of x for that piece. But then for the other one, you might look at that and go, oh my God. But it's not terrible if we do another substitution. I'm not going to do, I'll do u, it's a different u. But if we let u equal the square root of x, then du is 1 over 2 square root of x dx. So that integral itself, we're now going to have cotangent of u times 2. And so that one we can get pretty easily. If you probably don't remember the integral of cotangent, right? Is that an okay assumption?
Yeah, that's fair.
Okay, and there's no judgment here, by the way. So, but here's what you can do. Just turn that back into a cosine over sine. And then you can see that this is another, like, real quick u substitution. So this gives us 2 natural log of sine of u. And yes, I know plus c's, but don't worry about that. So then if we put it back in, this will give us 2 natural log of sine of square root of x plus 1/2 natural log of x. So that's that integral of the p. So now we need to go ahead and find our integrating factor. So here would be your next step. I'm going to erase this bit. So we need e to the negative of this. So e to the negative 2 natural log of sine square root of x plus 1/2 natural log of x. Let me bring the powers in. So we get e to the negative natural log of sine squared root x plus the natural log of square root of x. And then I'm going to use the product rule of logs to combine those. So we get the square root of x times sine squared root x. And then the minus brings that as a 1 over, the natural log cancels. So we get 1 over root x sine squared root x. Okay, so where are we? Where are we in the stages of solving this thing?
So that's z, and z, is looking at the wrong problem. So it's like, and then z is u prime, right?
Okay, so this is z, because remember, we're solving this guy, this linear first order, and we know that this process gets us to the z. I mean, there's again a plus c, but this is z. So then u prime is equal to this. So if we've got u prime equals that, then u is going to be the integral of 1 over root x sine squared root x, which, let me just rewrite this as the cosecant squared of root x over root x. And let's do another substitution real quick with that root x business. So let's call it t, let t equal square root of x. So we can do kind of the same thing and get a cosecant squared of t. The derivative is going to be 1 over 2 square root of x. So that just means we need a 2 here. Whew. All right. So now we get to integrate this. But it's actually a pretty easy one. That's just -2 cotangent of t. So we put in our root x. All right, so there's our u. But then what do we do with u?
We multiply that by our y1 to get the y value.
Okay, so now we're going to multiply this back to our y1. So u times y1, because remember that was the whole point. We're going to get minus 2 cotangent to the square root of x times sine of square root of x. And of course, cotangent is cosine over sine. And the -2, we don't really care about any constant multiples since we're just trying to create a basis for the solution space. So that's where we can just say, okay, y2 is cosine of square root of x. So that's where it comes from. Or you're just really good like Trey and go, well, clearly if there's a sine of root x, there must be a cosine of root x. Anyway.
Hey, Bruce, on the test for these second order differential equations, once we get it down to a first order differential equation, can we just throw that in a differential equation solver?
Yeah, that I don't mind.
Okay.
Because by this point, like with that one with the z, I know you know how to solve those, right? We've talked about them a billion times, and I'm fine with kind of using that as your shortcut.
Okay, thanks.
So, yeah, you're welcome.
Can we go over number 28 too?
We can definitely look at number 28, sure.
Thank you.
So any other questions on this one before we step away from it? But yeah, like it's just a lot of calculus. If you look at this, it was a lot of integrals, and it was things that are not ones that we generally remember right away, like integrating cosecant, for example. All right, so you also want to look at number 28. Is that what you said, Wes?
Yes, please.
Okay. Let me go take a look at it. Which section, real quick? 5, 6?
Yeah.
Okay. That's what I thought. I just wanted to make sure. All right, so same kind of story, just a different differential equation. So we've got 2x plus 1 times x times y double prime minus 2 times 2x squared plus 1, or sorry, minus 1 times y prime minus 4 times x plus 1 times y equals 0. And we're told our first guess, y1 is 1 over x. All right, so we'll go as far as I feel like doing this. At some point, I might just punt on it and go, okay, well, you guys know what to do from here, but at least let's get it set up. All right, so here's our y1. It's 1 over x. So to find y2, same idea. Let's do u times y1. So we're going to y is equal to u times x to the minus 1. So y prime is u prime times x to the minus 1 minus u times x to the minus 2. So then y double prime is u double prime times x to the minus 1. We're going to get minus 2 u prime times x to the minus 2, and then plus 2 u times x to the minus 3. And as always, please check my steps, because we don't want to run into what we ran into last time where there was some error and it was 5 erasings of the board prior. All right, so good so far? All right, well, let's put these into the differential equation. So we're going to have 2x plus 1 times x times our y double prime. So that's going to give us 2x plus 1 times u double prime the u's, we're going to get minus 2 times 2x plus 1 over x, so times u prime. And then the u's, we're going to get plus 2 times 2x plus 1 over x squared. So that x just changes all those powers by 1. Otherwise, I put in the 2x plus 1. All right, so then with the y prime, we're going to get minus 2x squared minus 1 over x. So minus 2x squared minus 1 over x times u prime. And then plus 2x minus 1 over x squared times u, because the minus minus. And then lastly, we do the minus 4 times x plus 1 times y. So that's going to give us a minus 4 times x plus 1 over x times u. All right. So let's see how that simplifies. So we're going to get 2x plus 1 times u double prime. In terms of the u's, let's see. We get a minus 2x squared minus 4x minus 2 plus 1, minus 1 over x times u prime. And then the other one should all cancel. and it doesn't. What'd I do wrong? You guys were supposed to catch my algebra mistakes. And of course, I've already erased those y's. So look back. Do you see anything that I did?
I'm checking the derivative and seeing anything wrong with them yet.
I'm going to pause the recording for a second. Okay, so we went back and we double checked our calculus. We saw that there was a sign issue, which then actually simplified that thing down to 2x plus 1 times u double prime minus 4 times x plus 1 u prime equals 0. All right, so by reduction of order, we can do the same thing where we did that we did last time with the z equals u prime. So this becomes 2x plus 1 z prime minus 4 times x plus 1 z equals 0. And if we get into the right form, we're now ready to integrate this guy. So I think this is where I'm going to stop us because we know what to do, right? We're going to get that z is equal to e to the integral of 4 times x plus 1 over 2x plus 1. Remember, it's the negative p. And then once you find that z, integrate it to get u. And then once you have that u, multiply it to the 1 over x, and that'll get you your other form. So is that good enough for you, Wes, at this point?
Yeah, perfect. Thank you.
Cool. All right, so I guess the moral of the story with these is that there are a lot of steps, a lot of places where you can definitely go wrong. Clearly, it's the pluses and minuses have always been one of my Achilles heels. So watch out for that. Just take your time. And there are definitely a lot of steps. But I am going to echo what Trey said earlier when he asked about on an exam. Definitely, once you get here, it's fine if you want to throw it into a differential equation solver or something and just jump to the, or write this step and then write z equals, and do your thing. That's totally fine. All right, so good for the homeworks. So reduction of order, I mean, it's really handy because it brings us back to first orders, which are really fast to solve. And it's just like anything in math. Really, our goal is, can we do it? And if the answer is yes, we can, then we're good, right? So this is a way to get it to a form that we can So, all right, so you still have that homework set on variation of parameters, and I know we'll talk about that next time. But we are going to go ahead and move on to the next section, in the next chapter, really, chapter 6, which now we're going to start applying this stuff. So I want to grab something here real quick off of my physics shelf. What I love is that my son's bedroom, this bookshelf that used to have Legos and Rubik's Cubes and all the other nerdy things that he had, has now been transformed into a shelf of physics toys. So basically, we traded his nerdiness for mine. So, and this is my older son, who's not really much of a physics guy. Like, he likes math and science. Well, he was good at math and science, but he ended up studying political science and communication. I don't know where I went wrong. So anyway, so let's come back and look at this. So all I've got here is a nice little spring with a little mass hanger on it. And I'm going to give it just a little bit of weight. Put some grams on here. So I just put 40 grams on this. And so this spring is now in equilibrium. And of course, if I pull it down and I let it go, it's going to start oscillating up and down. And when we first learned about this, when you first learned about this in physics or wherever, you were taught, okay, that's just a nice sinusoidal motion. You can use a sine wave or a cosine wave to describe it, and everything's good. But what was the problem with that model?
It will lose energy as it goes on because there's dampening, just environmental variables that will just affect the total energy within the system.
Yeah, like when you first built the model, there was that always same assumption of, let's not have any air resistance, let's not have any friction, no energy loss, and that sort of thing. But what we know is that that's not actually a good model, because over time, this oscillation will stop. You know, and I don't know if you can notice just in this time so far, but the amplitude of this oscillation has decreased. It's definitely not going as far up and down as it was earlier. And given enough time, we would see it eventually slow down and stop. Okay, so when you first learned about this back in the day, we didn't include all of that because it made the math way too hard, right? If you just look at this in terms of no air resistance and all that, it does turn into something really, really simple that we can get the solution to, and it turns out to be a sine or a cosine. Okay, well, let's take care of this today. Let's actually put into this model things like drag. Let's put into it forcing functions. Like right now, we're saying that there's, you know, even if we were to include drag, that's still kind of a simplification, because what if all of a sudden there was like a fan blowing down the whole time? Or something that was causing a repeated tap, right? It's going to change the motion because there's some sort of a force being applied. And as soon as we do that, our basic model goes out the window. So let's jump to the board and look at how are we going to deal with this when other things are involved. All right. So let's just start with good old Newton's laws. And we'll start easy. Let's not even have the spring moving or anything. We'll have a mass hanging off of it, but it's going to be stationary. Okay, so here's our spring. It's got some sort of a mass hanging on it, but it's going to be in equilibrium. So let's think about the forces that are going on to this block, this mass. So as always, we've got gravity pulling it down. But there's also going to be a force that's pulling it up. And I'm just going to call this the spring force. So in a situation like this where it's static, okay, so nothing's going on, we've got that the spring force and the gravity force are going to cancel each other out. Okay, so if we were to just use Newton's second law, we've got gravity pointing down, and I'm going to have down be my positive. But the force due to gravity is just good old m times g. So it's the mass of that object times the gravitational constant acceleration. We're going to subtract the spring force. So I'll just call that F sub s that equals 0. And do you remember how to calculate the spring force?
Isn't it using Hooke's law where it's like K times where K is the spring constant, yada, yada, yada.
Yep. And that's exactly what we're going to do. We're going to use Hooke's law. And what we know from Hooke's law is that the force of a spring is equal to minus kx, where x is how far it's been stretched. And so I'm not going to call it x, I'm going to call it L. And basically L, if we just had the spring itself, if we just had the spring itself, would be like this long. L is just the how far this got stretched out. Because for a spring, its restorative force is proportional to how far it's been deformed. Okay, so we know that this is the case when it's static, when it's not moving. All right, now you may be wondering, why did we look at that? Well, it's going to help us out when we go and we actually look at what happens when it's not static, when we've got the motion and we take into account things like drag and forcing functions. All right, so I'm actually just going to write this up at the top so I don't erase it. We've got that mg is equal to k times L. Okay, so now let's go to the dynamic. So I'm just going to change this picture a little bit. Write dynamic, which means that this thing is moving up and down. So it's still going to stretch and all that. But let's do two things. One, let's allow for some external force. So I'm going to put on here, it's going to be pointing down, but it can be pointing any direction. So I'm just going to write here, external force. So this could be the wind blowing, the tabletop shaking, the, whatever. Okay, but we're going to allow for something. So there'll be an external force. And then the other thing that we're going to have is now there's also going to be drag. So I'll put on another arrow. I'm going to point this one up for right now. But that drag, it doesn't necessarily have to be pointing up. The thing about the drag is that it's always going to be pointing in the opposite direction of motion. So this thing is moving up, drag is going to be pointing down. If it's moving down, drag is going to be pointing up, and so on. But if we wanted to be a little bit more general, here's how we could do it. We could just look at all our forces. We're going to have gravity plus the spring plus the drag plus the external force. And that's going to equal the total sum of forces, which by Newton's second law is equal to m times a. Okay, so good old just F equals ma. Okay, well, let's start simplifying this a little bit. So our mass times acceleration is going to equal our gravitational. So that one's going to be mg. And that one is pointing down. So I'm definitely going to leave it as going down. Okay, the force due to the spring, that's going to be minus k times how far it's been deformed. Okay, well, let me just do that as L plus y. So why is it L plus y? Well, as soon as I put the mass on, it stretched it by a factor of L. And then I'm going to add to that whatever the y is. And that's going to change. Y is going to be distance away from equilibrium. So remember that this is a function of time. So far, the things that are functions of time are acceleration and y. All right, so there's our spring. So then I need to add something for the drag. Now, drag is going to point in the opposite direction. So it's going to be a minus. And it's going to point in the opposite direction. And we're going to say that it's proportional to the velocity. So let me just write that up here. So you may remember that when we did air resistance of falling bodies, we made this assumption that we went with air resistance was proportional to the speed. It's the same kind of thing here. And again, this is why it's negative, because it points in the opposite direction of travel, and velocity points in the direction of travel. All right, and then we need to have our external force, and that external force, I have no idea what it is, so I'm just going to call it F, but I'm going to put a T. So let me just kind of highlight the drag was the minus gamma times V, the spring force, that was the minus K times L plus Y, and of course the external force. I just gave it a name, F. So this is what physics would say in terms of the force diagram and what has to appear. All right, well, I can simplify this still further. If you look at the bit from the spring that involves K, there's a minus K times L. Well, mg minus that KL is equal to 0. That came from the static part of this. So that's going to go away, and we're left with minus ky minus gamma v plus f of t. I'm going to move everything over but the forcing function. So we get m times a plus gamma times v plus k times y equals that f of t. And it's probably this point, hopefully, where you recognize what's going on. We know velocity is the derivative of y. We know acceleration is the second derivative of y. And so the next thing you know, we've got this differential equation. And so as soon as we incorporate drag, this thing turns into a linear second order. And even better, it's got constant coefficients, right? M, the mass of this thing, is always the same. The drag coefficient, as long as the medium that we're oscillating through doesn't change, that doesn't change. And K is your spring constant. Well, it's in its name, right? It's a spring constant. All right, well, there you go. So if there is no forcing function, like in the example that I just started with when I showed you the spring bouncing up and down here on my desk, that f of t is 0, this is just a homogeneous. Super easy to solve. If we put in some sort of a forcing function, well, that's going to require variation of parameters or reduction of order or whatever. But we're going to be able to get it using our proper methods. And in fact, because of the fact that these are constant coefficients, then we know exactly what y1 and y2 are always. So, but let's just talk about in general what kind of solutions we could get. So since this thing is good old constant coefficients, let's create the polynomial. So we're going to get mr squared plus gamma times r plus k. And let's do it generically with the quadratic formula. So our r is going to equal negative gamma plus or minus the square root of gamma squared minus 4mk all over 2m. And so in terms of what kind of solutions we get is all dependent upon the gamma squared minus 4mk. Because here are kind of the three cases. First, if that's positive, then what we're going to get is a solution of e to the r1t and e to the r2t. So our fundamental set is going to be those two. So we're going to have two exponentials. And so just the homogeneous bit is going to be these. I mean, obviously there's going to be a plus whatever we get as a particular solution for a given forcing function, but that's what we're going to see there. All right, so that's case number one. Case number two is where that equals 0. And since it equals 0, this is going to be the case where we have repeated roots. So we're going to get e to the rt plus c2t e to the rt. But even better, I can tell you what r is going to equal. What's r going to equal in that case? Look at the generic quadratic here.
That's just going to be gamma gamma over 2m.
Yeah, it's minus, but yeah.
Oh,
so minus
yeah,
gamma
minus gamma over 2m.
over 2m. All right, so in that case, we're still going to get exponential pieces, but they're going to be the same powers, just one of them is going to have a times t. All right. And then the third case is where that's less than 0. And if that's less than 0, we're going to get a complex form. And so we're going to get e to the RT times cosine of omega t plus C1 times cosine. Of omega t plus C2 sine of omega t. And again, we can actually describe what these things are. R is going to be minus gamma over 2m, because that's going to be the real part from our complex bit. And then omega, that has to equal the imaginary part. So that's going to be the square root of 4mk minus gamma squared over 2m. And yes, I swapped those. So I've got the 4mk minus gamma squared, but that's because I'm factoring out the negative number that showed up from the inequality. All right, so basically, here's what's going on with the homogeneous. Let's just think homogeneous. So this is going to be unforced. There's no force acting on it other than the spring, gravity, and drag, right? So that's I pulled that spring down and I let it go. There are 3 things that can happen. One of these 3. Now, what you saw when I did that was the third case, because you saw it oscillating up and down. This e to the RT, notice that since r is negative, that's going to decrease as time goes on. And you can think of that as playing the role of or part of the role of the amplitude. So the amplitude is going to decrease exponentially over time. Well, that completely explains what we see. Okay, so that was the case that you saw with the spring on my desk. Well, let's think about what the other cases do. So let's look at the second case where the discriminant part of the quadratic was equal to 0. So we get exponential, but they both are negative exponentials. So they're decaying as time goes on. But we don't get any oscillation. So in that case, what's happening is we are approaching equilibrium as time goes on, but without oscillation. And the same thing happens in this other case with case number 1. It turns out that both of these are going to be negative roots. And let's talk through that for a second. So just look at this bit. If gamma squared minus 4mk is greater than 0, I know that gamma minus 4mk is less than gamma squared. Are you guys okay with that statement? Since the mass has to be positive and the spring constant has to be positive. So I know that that's less than gamma squared, which means the square root of that is less than the square root of gamma squared, which is gamma. So look at what I'm doing. Where the minus happens, I have negative gamma minus something else, that'll be negative. So we know for sure one of the r's will be negative. The other one, I've got negative gamma plus something that's less than gamma. Well, that also makes it end up being negative. So what we know for sure is that these are both negative. So that means that those also both decay exponentially. And so the same kind of story, as time goes on, we're going to approach equilibrium. But again, there's no oscillation. So a spring, when set in motion like this, is not always going to oscillate. It's just not. How it behaves is all dependent on the gamma squared minus 4mk. All right, this thing right here is super important because depending upon its structure, you'll get different kinds of motion. So think about what would have to happen for us not to get that oscillation. So basically, we need to make this gamma squared minus 4mk be non-negative. So we can do that in a couple ways. One, we can increase gamma. If gamma gets bigger, eventually gamma squared is going to be bigger than 4mk. Well, gamma, if you recall what that was, right here, that was our drag coefficient. So if the drag coefficient is high enough, you won't get oscillation. Well, think about me doing the same thing with that spring, but you know, it's in a tub of honey or something. So I down into the honey and I let it go. It's going to return up. It's probably going to be really slow, right? We'll see it slowly get up there. But it's not going to oscillate. It's not going to get to the point where it goes above equilibrium and get pushed back down and so on. So you can get that to happen by increasing gamma. You can also get that to happen by decreasing your mass or decreasing your K. So lighter mass, it's going to be less likely to oscillate. And the same thing with smaller K. The smaller K, I think, makes sense if you think about it. A smaller K means that the spring doesn't really want to, or the spring is easily deformed, right? And so there's not a lot of force, not a lot of restorative force. So basically what's going on there, if K is really small, you pull this down, the spring's like, yeah, whatever. I'm not trying to pull it back up very hard. So there's not much that's fighting against your drag. But it is a dance between these three quantities in terms of which of the three are going to happen. We have names for these different stages. So let me go ahead and give them to you here. So if gamma squared minus 4mk equals 0, we say that this is critically damped. And that should make sense. Like, think about what a critical number is. The same kind of idea. So that's the point at which weird things are happening. All right. If that's greater than 0, we call this overdamped. Which again, I think is a great name. It makes sense. So not only is it damped, but it's overdamped. It's to the point where we're doing more. So that's overdamped, which then makes you think that the less than 0, we call that underdamped. We don't actually usually call it anything. It's just damped motion. But if you want to think of it as underdamped, that's fine too. All right, so it's all going to come down to what are these three numbers? How are they related in terms of what we're going to see? So if we were to draw the graph of these different cases, this is kind of what you would see. So first of all, the just regularly damped, the one that leads to oscillation. we know that we're going to see bouncing back and forth, but the amplitude is going to decay exponentially. So let me just put on a plus or minus e to the minus something, okay? So think of this as e to the minus RT. This is negative e to the minus RT. What you're going to see in terms of your oscillation is something that's doing good old sinusoidal motion. It's just bouncing back and forth. It's trapped by those two things. So that amplitude is being decayed exponentially. Now, for critically damped and overdamped, what you can see, and again, it kind of depends on the numbers, but an example of one of those would be something like this. Here would be a graph of one that's probably overdamped. So this would be one where we like give it an initial push up, but it's so damped that as it comes back down, it never goes past equilibrium, right? Or it could go past equilibrium, like let's say we had pulled it up and gave it a push down. It might go down, but then come back up. So for those, for both critically damped and overdamped, it is possible to cross the axis, but it's not going to continue to bounce back and forth. It's basically going to settle itself down and approach zero, approach equilibrium. Okay, so there's the theory, at least in terms of the homogeneous. So let's talk a little bit about how we find these numbers. Now, the mass is usually given, but we don't always have K given, and we don't always have gamma given. So how are we going to find those numbers if we need them? Well, do you guys remember how to find K? Like if I gave you a spring, I'd take this same spring right here, and I just say, okay, I want to find K. What do you guys do to find that? So Thea, you're talking, but I can't hear you.
Find the amount of force, pull down the spring, check the distance that's stretched, and find the amount of force it's applying, and then solve for K.
Yep, there you go. So to find K, what you need to know is how much stretch occurs for a given force. So if you know that, if you're told, hey, a 3 Newton force stretches the string, or sorry, the spring by 10 centimeters, that's actually going to be enough for you to find your K. Because again, if you go back to that formula, K, it's equal to F divided by X. So you just take that force and divide it by how much it got extended. So if K isn't supplied, this is how you find it. Okay, so then what about gamma? What do we have to do to find gamma? Now this one I'm not going to ask you guys how you did it because you've never done this before, unlike a spring. But we're going to do kind of the same idea. Look at where gamma came from, right? We had that the drag force was equal to gamma times velocity, or gamma times speed. All right, so we got drag is equal to gamma times your velocity. So gamma is going to be the drag divided by the speed. So in order to find gamma, what you're going to need to know is how much drag at a given velocity or given speed. So in the situation where they don't tell you gamma explicitly, where they don't say gamma equals, whatever, if they tell you a drag force for a given velocity, then that will be enough. All right, so let's actually try one. Let's take a word problem here, and let's see if we can figure out the different values for K and gamma, and put those in and see what we'll get for our function. All right, so here we go. So I'm going to tell you that a 5 Newton force stretches a spring 4 centimeters. I know that there's a resistance. I'll put here resistance in the fluid is 6 newtons when the velocity is 1/2 meter per second. All right, and then we're going to do this. A 4 kilogram mass is attached to the spring. It is pulled down from equilibrium (10 centimeters) and released from rest. So what I want to do now is 2 things. One, let's actually create the differential equation. And then 2, let's solve it. Let's see whether we've got overdamped, critically damped, just plain old damped. Let's see what ends up occurring with this motion. All right, so this is the kind of thing you're going to see in your homeworks. So we're definitely in the word problem section of class. All right, so we have to find M, gamma, and K. And I know I didn't say it, but we don't have an external force here. Okay, there's not going to be any kind of a forcing function. So let's just go with unforced. Let's find M, gamma, and K. So the M, that was given to us. We have a 4 kilogram mass. So there's our M. So gamma, we're going to get gamma from looking at this bit. So we've got resistance in the fluid of 6 newtons when our speed is 1/2 meter per second. Okay, so gamma again was the drag force, 6 newtons, divided by the speed. So gamma is going to be 12. The units on that are kilograms seconds, by the way. Or sorry, kilograms per second. Don't worry about the units. This isn't physics class. All right, so there's our gamma. So then we also have to find K, but that's where this is going to come into play. Because again, we know that K is equal to the force divided by the distance. So I'm going to convert that to meters. So 4 centimeters is 0.04 meters. And that should end up giving me 125. And those are kilograms per square second. All right, so we've got everything we need. Let's create that differential equation. So we're going to have 4 times y double prime plus 12 times y prime plus 125 times y. And we're going to go ahead and go equals 0. All right, now you notice that I told you some other stuff, right? So it's pulled down from equilibrium 10 centimeters and released from rest. None of that mattered in terms of building the differential equation. It didn't matter where I stretched it or how I let it go. None of that mattered because none of that comes from the spring and the medium. Like all of these things are from the system, not how the system is behaving. So none of that will actually matter in terms of building this differential equation. But where does it matter? Why even have this stuff then? Well, they're the initial conditions. I just told you how far I'm moving it down. I'm telling you what speed I'm giving it at the beginning. So these things are important, but in the context of the initial condition. I've got y of 0 and y prime of 0. Right? I'm releasing it from rest, which means I'm not giving it any velocity. So y prime of 0 is 0. I'm moving it down, so I do have an initial position. I'm moving it 10 centimeters, so it's going to be 0.1. But the question is that positive or negative? So is my initial condition there y of 0, is it a positive 0.1 or a negative 0.1?
Didn't you, in the original equation, didn't you define down to be positive? And it says it's being pulled down, so it would be a positive number,
That
right?
is correct. Good catch on that, Thea. The way that we built this equation, that was down. Down was positive. So it is going to be y of 0 equals a plus 0.1. Had I actually pushed it up from equilibrium, then the initial position would have been negative. All right. Well, there's all the information from our word problem. And now we're ready to go. So let's start by looking at, is this thing going to be critically damped, over damped, just plain old damped? So let's look at gamma squared minus 4mk. So that's going to be 12 squared minus 4 times 125, which is 144 minus 2000, which is negative 1856. All right, so you should be able to tell me what kind of behavior we're going to have. What's this thing going to do?
it's going to be a oscillation. So
Exactly. So this one's going to oscillate. And so it's going to be damped oscillation because we got a complex root here. All right. So let's get what our form looks like then. We're going to have y equals. So we're going to have a negative exponential. And that negative exponential is going to be negative gamma over 2m. So that's minus 12/8, which is the same as minus 3/2 or minus 1.5. So we're going to get e to the minus 3/2 t times C1 cosine of, okay, well, it's going to be the square root of 1856 divided by 2m. And that's all going to be times t. Now, that probably simplifies. In fact, yeah, you can definitely divide that top number by 4. You can divide it by 8. Oh yeah, you can divide it by 16 as well. Let's see, that gives you 125 minus 9 is 116. So let me reduce it.
it's 8 root 29.
8 root 29 on top?
Yep.
Is that after dividing by the 8?
No, that's not.
Okay. So then it'll just be root 29. Right? 8 root 29 divided by 8 is root 29?
Yep.
Okay. So we're going to trust these numbers here. So there's C1 cosine of root 29t, and then plus C2 sine of root 29 times. So we see it, we see the oscillation, but with the exponential decrease. But now let's use our initial conditions to find C1 and C2. So when we plug in 0, we get a sine of 0, which makes that go away. We get a cosine of 0, which is 1. We get e to the 0, which is also 1. And so from our initial condition, the y of 0 equaling 0.1, that gives us that C1 is equal to 0.1. So then to get C2, we have to use the fact that we were starting at rest. So that means we need a y prime. So it's going to be minus 3/2 e to the minus 3/2 t times C1 cosine root 29t plus C2 sine of root 29t plus e to the minus 3/2 t times, well, minus root 29 C1 sine of root 29t plus root 29 C2 times cosine of root 29t. And now let's plug in our 0 there. So if we go to y prime of 0 equals 0, that tells us 0 equals, well, we're going to get minus 3/2 times C1 times cosine of 0, which is C1 plus 0. And then when we plug 0 into this next bit, we're going to get 1 times, well, the sine of 0 is 0, and the other one we're going to get root 29 C2. So C2, it should give us 0.15 over root 29, whatever that happens to be. So let's just replace those up here, and I'm definitely too lazy to rewrite that whole business. But this is going to be 0.1 cosine plus 0.15 over root 29. All right, well, there you go. You now can handle damped motion in a spring. So let's think about what else happens though when we've got this damped motion, because we're combining a sine and a cosine. We're actually adding those things together. And you may remember, if you don't, I'll just remind you, that when you add sines and cosines together, you get other sines and cosines. And so instead of having it all written like this, we can actually figure out the new amplitude, the new period for these things. But it turns out that the period itself is what we call a quasi period. It's a quasi frequency because the motion isn't exactly periodic. When I showed you that spring bouncing up and down, it actually wasn't regular oscillation. The period changes a bit. So we call it the quasi period, quasi frequency. But let's start with undamped. Okay, so let's look at what happens if this is undamped. So in undamped, that means gamma is equal to 0, which changes this guy to my double prime plus ky equals 0. And this one is going to give you complex numbers, but it's going to be purely imaginary. There's not going to be any real part to it. And so this one, you're going to literally see oscillation, like always. Okay, so basically what we're going to get here is that y, it's going to equal just some sort of a C1 cosine of omega t plus C2 sine of omega t. And what we know about omega is it's the square root of k over m, if you do the math on it. So that's omega, which means then that the period, I don't know if you remember this, but the period, it's equal to 2 pi over omega. And so the period of an undamped motion, it is regular, but it's going to be 2 pi divided by this, so that's 2 pi times the square root of m over k. So in the undamped world, we know exactly what's happening with this. It's 2 pi times the square root of m over k. That's the period. We also can get the amplitude. So if we wanted to, we could rewrite this as y equals A times cosine of omega t, say minus phi. We just go to the allowing a phase shift and all that. And I'm not going to bother you with the derivation. It's just from some trig. But it turns out that that amplitude, it's the square root of c1 squared plus c2 squared. And if you want to know the phase shift, the tangent of that phase shift is equal to c2 over c1. So basically, in an undamped world, it is sinusoidal. Its period is the same period as the individual pieces that comes from the square root of k over m. And then the amplitude and phase shift happen here. And the one other thing I want to share with you is a name. There's something, and I think I probably have said this in the past, but we call this the natural frequency. And notice that it's just dependent on the system. You tell me what mass and the constant for the spring. There is a natural frequency for that because of the structure of the system. And this is important, as we'll see later when we talk about things like resonance and all that. The natural frequency is one that, if we have a forcing function with that natural frequency, weird things can happen. Okay, so that's our undamped. Now, if it's damped, we've already seen, like we've gone through the derivation of all the different things that can happen. But what changes there is our frequency. And so let me show you what happens now. So if we go back to damped, so gamma is not equal to 0. Now what we get is what we call a quasi-frequency. So again, this is how we're bouncing back and forth, up and down, but it's not regular. Okay, it's not actually the frequency because it's not periodic, but even though it changes, we can still find it. And again, I'm not going to go through the derivation and all that, but I will show you how this holds. If we call this quasi-frequency mu, it turns out that if you, well, I'll just show you what it is. So mu, it's equal to the square root of 4km minus gamma squared divided by 2m. Right, that was the one that we called omega before. Right? But this, it's not exactly a frequency. So it's a quasi-frequency. But if you look at this guy and compare it to the omega for the undamped, so if you just kind of look at the ratio of those things, this is the square root of 1 minus gamma squared over 4km. And the reason I wanted to show you this is because it shows you how the dampening affects that period, right? So if we're in the situation where there's no dampening, gamma equals 0, this goes away, and we get that the ratio of these is 1, meaning they're the same thing. Okay, so your quasi-frequency is your frequency if you're undamped. Now, we also know for the different situations, this gamma squared and 4km, it's kind of a big deal, right? Like critically damped, what happens to this? What does it mean for it to be critically damped?
It just goes back to equilibrium, right? Or it starts out at whatever starting position and it just goes back towards equilibrium.
Yeah, so there's no oscillation, right?
Yeah.
And in terms of these numbers, gamma squared equals 4km. If that's the case, this is 1. 1 minus 1 is 0. And so that tells us then that mu actually is 0. There is no frequency once we get to critical damping. Well, duh. Right? But it's nice that the math actually follows that. All right, so you got a quasi-frequency. You also have a quasi-period, which is just this thing flipped over, right? But that's what's going on as soon as we allow dampening, because we still get something that's sinusoidal, just not quite the same. All right, I think this is a good place to stop. I know we still have a few more minutes, but I think instead of going into more examples, we'll break it here. So what we'll do next time is we'll look at the forcing vibration. What happens as soon as we have a forcing function? In terms of solving it, it's no different than what we've been doing. We're just going to have to do either, variation of parameters or insert favorite method here. But allowing a forcing function does change things a little bit. And I definitely need to talk about that. It's more than a 5-minute conversation. So that's what we'll do next time. In addition to looking at electricity, we'll start looking at circuits, and we'll see how we can generate the same kind of functions there. All right, so anything else before we go off the record?
Not really.
No.